Students, a good day to you. Today, we are going to discuss about the topic seismic waves. So, the last class we had discussed what are all seismic waves and how it propagates, all the things we discussed in the last class. In this class, uh, we are going to discuss about all the details about seismic wave, how it forms and where it originates, and what is the reason for this propagation, how it propagates through the medium like solid and liquid. All the things we are going to discuss it today. And today is a very important class because in the last class we saw only just an introduction, but this is an in detail explanation of how seismic waves and how we can map these seismic waves with the seismograph, all the things we are going to discuss. So it will take 1 or 2 classes to complete the entire seismic waves. Today, let me start the presentation with the I will stream the PowerPoint. I hope it's visible to you right now. Seismic waves part 2. So we need to discuss about this seismograph. Seismograph. So seismic waves, when it propagates, what will happen? The earth will shake. So this movement, which can be mapped using this seismograph, the recording can be done using this seismic seismographs. So it's just a graph, and this graph will explain how much magnitude and where it happens, and what is the intensity and what is the ground acceleration. Everything can be obtained using this seismograph. But before going to the seismograph, we need to understand what is a primary wave and what is a secondary wave, and how it propagates, and why it propagates so fast, and the why the secondary waves are moving slowly than primary waves. All the things we are going to discuss. The seismograph is a device to record the seismic waves. So in which it contains a spring, which contains a long the spring connected with the moss which contain a needle which can record the vibrations. How it works? It is based on the Newton's first law. So first law of inertia. So when there is a motion, the ground motion is there, it takes some time, and the ground moves. When the ground shakes, the bob also will shake along with the ground. So that makes the recordings in the seismograph sheet. So it's a graph sheet. It's a vertical. Why we require vertical and horizontal? Because the ground will shake horizontally and vertically. Sometimes it will be horizontally and it will be up and down. That is vertically up and down also. It will move. So this is a zero massless spring. We call it as a zero massless spring, and this factor also can be considered while calculating this equation, and this will record the seismic vibration. This is a modern seismometer. So apart from this conventional seismometer, as you see in the last slide, it is a modern seismometer which contains the electromagnetic force holding a mass in place and measuring the current required to do so. For example, we can take a piezoelectric sensor. If there is any mechanical vibration, the electrical signals can be generated. So that is the inverse piezoelectric effect. If there is a mechanical vibration, it will produce the electric signal. So if there is an electric signal, it will produce mechanical vibration in the form of ultrasound range. So ultrasonic range, it will produce electromagnetic. It will produce waves, mechanical vibrations, which is in ultrasound range. So likewise, the piezoelectric sensor can be placed so that the vibrations can be detected, and this vibration in turn, which in turn converts into the electrical signal, and the electrical signal which records this uh, seismic signal in the seismograph. So before going this, I want to tell you one thing, that is seismograph is it's a graph to display what are all the waves coming in and how much magnitude is there. This is the seismograph. Seismometer is a device or instrument to record the seismic waves. Seismic waves means it's an earthquake waves which is generated due to the movement of a tectonic plates. Okay, so be clear in that. So let us move on to the next slide. Three components of motion in the seismograph, that is east, west direction, north, south, and up and down. So three things will be recorded in the seismograph. If you speed it up any earthquake signal and listen to it, it will sound like thunder because of the rattling sound of rocks. You can hear it. Okay. So this is the original recorded station 1, station 2, station 3, station 4, station 5, which is at a particular distance. So it varies. The time will vary. So the universal time 1552. What the time? Universal 1552. In the seismic wave originated in 1996 of January 14th, 1996, magnitude 1.7. It has been recorded. So this record is different at different stations. Then how can we estimate? So all things we are going to discuss in this class. So each station record these vibrations at the different time intervals, isn't it? Why? Because the seismic waves, it takes some time to travel from one distance to another distance. That is in terms of station, one seismograph station to another seismograph station. For example, in our Lila College, we are having one seismometer, if you assume. The next seismometer, if I have located this next seismometer to some other SRM University or somewhere else around Chennai, it will take some minute seconds, that is a very, very, very small fraction of seconds to travel. So the fraction of seconds can be calculated, that is the travel time of a seismic wave. For example, in our college, if you are having a seismometer and the next seismometer, which is located in Andhra University, then the seismic wave, it takes some time to travel from here to there. Sometimes it may travel from there to our college also. So we cannot estimate the travel path of a seismic wave. It depends on the geological parameter of Earth. So this is exact seismograph. So each station, the graph will vary. So you can see that first initially the peak is much less. That is what we call primary waves. And the peak, when it rises, that is the secondary waves which reaches the peak station. So this is the fundamental of a seismograph. So graph, you can see that is it contains x and y axis. So x axis, which is a time in seconds, and y axis, which is the magnitude or amplitude of the seismic signal. Okay. So the next one, different kinds of waves exist within a solid materials. We call it as a body wave and surface wave. So generally, we call it as a body wave which propagates throughout a solid medium. Body wave means inside the body of Earth. How the seismic wave travels, we call it as a body waves. Surface wave, which is propagated at the interface between the media, that is a surface wave on the surface of the Earth, how it propagates. So, this primary wave P wave motion, which contains the compressional. We call it as a compressional wave, which compresses and dilates when it travels from one place to another. S wave, we call it as a secondary wave or the shear wave. The shear wave, which is traveling along the direction which shears the path. Okay, so the body waves and surface waves are the classification. So P wave, which is the direction of propagation, that is along the direction how it propagates. The particle motion will be left and right. Okay. A S wave, it's up and down. The direction of propagation is this like this. The particle motion will be up and down. Okay. So we call it as a compressional wave, that is a P wave in two dimensional. Shear wave, that is a S wave in one and two dimensions. So different types of waves have a different speeds. We have the equation of shear velocity and compressional velocity. Can you say what is the shear velocity? Yes, shear velocity is due to the secondary waves. Velocity due to the secondary waves. Compressional velocity, which is due to the primary waves. So the primary waves, which plays the major role in compression and dilation of the particles. Okay. Now, what is this velocity of a shear wave? That is the root of nu by rho. That is, nu is the shear modulus or shear stress by shear strain, and the rho is the density of the material. And the second equation Vp, that is due to the primary wave velocity, compressional velocity, which is k plus 4 by 3 nu by rho. K, which is the bulk modulus, that is the three-dimensional variation of this stress. So we call it as the bulk modulus. So why we are talking about modulus of elasticity? Because this, whenever there is a force applied on a material, it acts like a elastic rubber band. So it can be, when a stress is applied on it, strain will be there. So that is a fundamental of a Hooke's law. So within the elastic limit, Hooke's law states that within the elastic limit, stress by strain is constant. So here, Young's modulus means linear stress by linear strain, and bulk modulus means volume stress by volume strain. The bulk, the entire volume. But the rigidity modulus, which is the shear stress by shear strain, we call it as the rigidity modulus. So nu, which is the rigidity modulus of the rock surfaces, the rock structure. So how much pressure, how much stress, we call it as a stress, which is the force per unit area, that is the pressure. It is nothing but the pressure. So pressure, the formula is force per unit area. So the stress, which is the pressure that is being applied on a material, how much it deformed after the pressure being applied, that is what we call strain. So the rigidity modulus means shearing stress by shearing strain, that is nu. And the volume stress, the entire volume, the three-dimensional volume, how it changes, how it deforms, we call it as a bulk modulus. So always P waves travel faster than S waves, and both travel faster than surface waves. So P waves get there faster. The seismograph record and the pathways have three types of waves, seismic waves: primary wave, secondary wave, and surface wave. So primary wave. So what time? It is not exactly 0 to 30 minutes. If it is 0 to 30 minutes, within 30 minutes, the people can escape. But unfortunately, it's not like that. It's only in seconds. It is for the demographical view. We want to explain how it moves. So this is the graph where the P wave and the focus. Focus means that the point where the earthquake which forms the earthquake form. So when it travels the path like this, and the primary and secondary wave will reach. Okay. So as well as types of surface waves are there, that is Rayleigh wave and Love waves. So as well as the body waves, there are surface waves. So body waves means the waves which are traveling inside the earth. Body waves. The primary wave and secondary wave are the classification. And the surface wave, there are two types, Rayleigh and Love wave. That is along the surface. So the Rayleigh wave, the particle motion will be rolling motion, like a tide, it will roll. The particle motion will be. The love wave, which brings a lot of destruction, because the particle movement will be left and right and up and down also. So this love wave and Rayleigh wave are named after the scientist Rayleigh and Love. Love is a British scientist who discovered this kind of waves. So at this juncture, I want to explain you the basic classification of this waves. First, body waves. The body waves means the seismic wave which are traveling inside the body of Earth. That is a primary and secondary wave. So body waves under the heading we have primary and secondary wave. And the next side heading is a surface wave. The surface wave which travel on the surface of Earth, which can be classified into Rayleigh and Love wave. So general classification is body and surface waves, and the subclassifications are body waves. We have the primary and secondary, and surface wave. We have Rayleigh and Love waves. I think you are clear in this classification. It's very important. So, a network of seismometers all recording earthquakes, as you see, the primary wave arrival and secondary wave arrival are like this. So there is a time lag between the S and P waves as the distance from epicenter. So hypocenter is the place where the earthquake originates, and the epicenter is the place where the earthquake happened on the surface of the earth. That is more important. On the surface of the earth, how the earthquake waves, where the earthquake waves originated, that is more important. Whether it is inside the ocean or on the landmass. So the seismograph located at A, B, and C, where you can see the time lag. So the A position, we have the P wave arrived much earlier than B than C. So three different locations of seismograph station which records this waves. So this is a very important graph, travel time graph of seismic waves. So this travel time graph, which explains how much distance the P wave is there and how much distance S wave is there and what is the time lapse. This graph is enough to explain where the earthquake is happened and how much distance it is there from one station to another. We can estimate it. So this is a standard graph. So the yellow line, they draw this line based on the velocity of P waves. How much speed it takes from 0 to 10,000 kilometers if the P wave originates at the point 0 and it reaches 10,000 kilometer, how much velocity is there, then how much distance it can cover and how much time it will be there. So as you know, distance is speed equal to distance by time. So based on that, we can estimate the graph. So the P wave have a particular velocity, as you said, as you see, Vp equal to root of nu by rho, and S wave which has a particular velocity, that graph will be like this. So if you are having the seismic station at a particular distance of a epicenter from an epicenter, this is the epicenter distance where the earthquake originates. And if you are locating around 200 or 1000 kilometers, and we can plot it and we can find the time interval between P and S waves. If we know the time interval between the P and S wave also, we can determine at which place are you, and the seismograph station located at different station, how the time interval will be, we can estimate it. So this is a very, very standardized seismic travel time curve, which can be used to measure this travel time and the distance between the epicenter. For example, if there is any earthquake happen in Japan, then how much distance is from Japan to India, and approximately we can estimate the primary and secondary waves. We can map it. Unless we don't know this graph, it is very difficult to map the distance between these two stations. And moreover, if you have the primary and secondary waves, we can find the epicenter also. So I can rotate this graph and I can see this primary wave and secondary wave distance. I can take this graph and merge it with this plot, and I can find the distance also. From the epicenter, it's around 5,000 kilometers from here. So there's an earthquake happened. So like that, I can estimate it. So this is a very important graph to track the location of the earthquakes. So this is very important. But locating the epicenter, only one station is not enough to make the precise location of the epicenter. We require at least 3 seismograph stations to record and to find the primary and secondary wave distance and to record, and based on that location we can estimate the epicenter. So the previously we saw this place. If this is located in at this place, it will not be correct. We need to take at least 3 locations. Minimum of 3 locations are necessary to locate the exact position of a epicenter. That is very, very, very necessary. Like we are determining the location of spatial coordinates, that is latitude and longitude, using 4 satellites. So at least 4 satellites are required to locate you precisely. That is in latitude and longitude where you are located. I need to have 4 satellites at least to measure the location, exact location. Likewise, seismograph station, we require 3 seismographs to record the seismic waves. To determine the epicenter, we need to plot it and we need to find it. Okay, that is very, very important. The first motion of the earthquake signal has information about the motion on the fault that generated in it. So that is a crack generated in this rattling sound of a rock. So that is a crack generated. Next, the orientation of faults can be determined from seismic networks. Fault means initially there is a crack on the rocks, so that cracks which produces the earthquakes, and that cracks or fault that develops and form a bigger earthquake. The orientation of faults can be determined from seismic networks. So the orientation of fault plane dictates first motion on an array of seismometers. So the compressional and dilation of a compressional wave. So how this seismic waves propagates. So this is very important. So any change in wave speed due to the composition change with height will cause refraction of rays. So the wave can be reflected and it can be refracted also. What is reflection and refraction? So reflection, so if there is an incident ray, it will bounce back. That is, it reflects back. Refracted, when it moves from one medium to another, it travels in a different path. We call it as a refraction. So, for example, P wave propagation is like this. It's in two-dimensional. The P wave propagates and refracts and reflects on the surface like this. So, on the boundary, reflection and refraction at a boundary, the wave propagates like this. So, the surface waves, that is a love wave and Rayleigh wave, and how it propagates, it can be recorded like this. So, these are all the insight relationship between this refracted and the reflected rays. So seismology can be used to infer the structure of the interior of Earth. That is a compositional layers. What is the composition and what are all the layers found in between? That is on the top surface, we have the continental crust that is 10 to 70 kilometers and oceanic crust that is 5 to 7 kilometers. And lithosphere is the layer of rocks 10 to 200 kilometer. There under these rocks, the aquifer and the good groundwater, all the waters will be available in this lithospheric region. Asthenosphere, it is the layer below this lithosphere and mesosphere, and the core, outer core, and the inner core. So this kilometer, which determines the inner depth from the top surface to inner depth, how much distance is there. Wave speed depends on pressure and temperature also. So depth varying the depth 0 to 2000, 4000, 6000 kilometer. How much the temperature and pressure, based on the temperature and pressure, how much it varies. Since velocities tend to increase in the crust, wave paths are curved due to refraction. So simple refraction to layers V1 and V2. So V2 greater than V1. So if there are several layers, the V6, the velocity, this will be greater than V1. So the velocity change is continuously a curved wave path. So if the earth were homogeneous in composition, the earthquake focus is there, the wave velocity will be curved wave, will be like this. If wave velocity continuously increases downward, all waves will travel along curved path, refracting back towards the surface. So if it is a homogeneous medium, but unfortunately, Earth is not homogeneous, it is not easy to determine the ray path of each seismic wave. Then what shall we do? So we need to have the understanding of what are the layers of Earth. So that's why seismic wave velocity at the crust, how much distance, how much speed is there, we need to estimate. And asthenosphere, how much speed is there, mesosphere, what is the speed, core, what is the speed, that is necessary. So S wave cannot propagate through core, leading to a huge shadow zone. How we obtain this shadow zone? Shadow zone is the zone where the earthquake waves cannot reach the seismic station. Why? Because the S waves cannot propagate through the core. So the S waves cannot propagate in a fluid. Fluid cannot support shear stresses. So that's why the outer core, which is in liquid form, which cannot allow the S waves to travel through it. So that's why, for example, if an earthquake happen at this particular place, here there is a station, seismograph station at Japan. Here there is a station at Atlanta. Here there is a station in Delhi. So what will happen? The Japan and Atlanta, which can record the seismic waves, but unfortunately in Delhi, it cannot record the S waves. That is due to the seismic waves cannot travel through the liquid, through which we have the understanding of the outer core is liquid in nature. Liquid in nature. So this is what we call the seismic shadow zone. The shadow zones. This is the entire picture of a shadow zone: P wave shadow zone and S wave shadow zone. So the earthquakes generated seismic waves that ripple through the solid earth. So these are all the P waves. When P waves hit liquid or partially liquid layer, they bend. They bend. That is what is the meaning of bending. In terms of physics, we call it as refraction. So refraction means when a wave travels from one medium to another, it bends. So we call it as the refraction. So when P wave reaches this side, it expels out some of the region. We call it as a P wave shadow zone. The P waves reach the solid layer, they bend again. All the bending of waves creates a shadow where no P waves reach seismographs on the Earth's surface. It is one of the biggest discovery in this seismology. That is in terms of the earthquake waves. It is a very, very important discovery. After numerous earthquakes, after analyzing more number of seismic waves, seismologists had an understanding that outer core is liquid in nature. That's why some of the region that is we didn't receive this P wave, and some region we didn't receive this S wave. The previous slide, you can see this is the seismic S wave shadow zone, that no S wave were obtained in the seismograph located at these stations. Here, this is a P wave shadow zone. So this P wave shadow zone has been obtained because of this bending of P waves when it reaches the core, outer core. So the pathways from any given source are constrained. So seismic phases are named according to their paths, and these are all the degrees. How much degrees it varies? 103 to 144 degree. So that is the variation of P wave to P wave shadow zone. So these are all the some important graphs about the travel time graph of a system. This is the original actual arrival times compiled from a global data. So travel time graph. So interior composition of Earth. This is the basic thing. Finding the mean density of Earth. The density of Earth can be obtained using this uh, small equations. So that's all for today. So um, let us wind up this session. And today we saw a lot of discussion about seismic waves, how it travels, and how it propagates, and all the things we discussed. And it is very important uh, for you to have the understanding and about seismic waves. So there's seismic waves. Um, there are we need a lot of understanding about seismic waves. See, if a disaster happen, if you see the real earthquake footage, it's really scary, really scary. So let us see some footages of earthquakes and tsunami and from YouTube. So it will be really something scary. So we need a lot of geologists and geophysicists to predict the earthquakes. So unbelievable damage. So I will show you some of the real footages of this real world earthquake happened. Wait a minute, I will stream the video. Watch this video. Okay, students, I hope you enjoyed this session. And if any queries or comments, you can post it in the classroom, or else you can comment in the YouTube comment box. So I hope you enjoyed the session. All the best, and have a nice day. And study well the seismic waves, as you are going to face the next internal examination it's very important to study this seismic wave classification. So two important questions will come from this. One is the classification of seismic waves and seismic shadow zone. Okay, all the best. Have a nice day, students. Thank you so much.